So the big three stands for the destructor, the copy constructor, and the copy assignment operator. Destructor is you cleaning up after yourself, right? And then the copy constructor is you're trying to make a brand new thing based on some other thing that you already have of that same type. It's like it's being born right now. You're constructing it. It's still a constructor. And then the copy assignment operator is similar to the copy constructor in that you want to copy somebody else into you, but you yourself have already been constructed at that point. Like you've got two things that have already been made that exist. A constructor has been called for all of them, but you come along, you're like, no, actually, I want this B2 thing to be the same as this B1 thing. And then you give meaning to what it means to be the same in the copy assignment operator. So we get some default things, and those default things copy the member variables. They copy those member variables, and sometimes that's fine. Sometimes it's good enough. Usually when pointers are involved, it's not good enough. All right, so we learned about all that fun stuff. So before we get started with more big three stuff, I just want to remind you of something that is a very common error that I see among CSCI 40 and 41 students. So, okay, this is fun. So let's say we have got a class that's very silly and simple. So the foo class, it's got a member variable called blah, and it's got a setter called set blah. And then this is the way that that is implemented. If I were to say foo f boop, that would make, there's no constructor. So the default constructor is going to keep the int set to garbage, right? So that would happen. And then if I were to say f dot set blah to 42, I would like this to happen, but it's not actually going to happen. Does anybody see the problem? Yeah. Anybody else see it? This is a very, very common error that I see. And this will get you. This will get you good. It's very hard to track down. The issue is you said int right here. Does everybody see that? Yeah. What happens when you say the type of something?
You're making a new variable.
You're making a brand new variable with that same name. That's disgusting. So, okay, so inside of set blah then, when we're calling it, like this gets called, on the stack, we have our blah member variable. If we just say its name, set it to something, that would work. But on the stack, if we say int blah equals x, that makes a brand new int variable called blah. So during that call now, we have two blahs, our member variable blah and this local variable blah. And of course, that takes priority because I just made that thing. It thinks you want that one. So that'll set this blah to the 42 that we passed into x. And then all this stack stuff is going away. The second set blah returns, and we never set our actual member variable. Does everybody see that? So that's a very, very common error that will just bite you. All right? So look out for that. Now you know. Another cool, or along these lines, you also have to kind of worry about the same thing in constructors, because I've done the kind of thing for you in the past lab where it was like, I gave you the name of, like, as a constructor parameter, I gave you the same name in the parameter as the name of your member variable, and that's very easy to do the same thing of like shadowing stuff. So like you had to use an initializer list to set the name of a member variable to the name of a parameter, then there's no ambiguity. So go back to that example, it's kind of fun to think about. So that's why you have to kind of use the initializer list. Because the first thing you say is your member variable, and the second thing you say is whatever takes priority, and it's going to be the thing that's closer to your parameter if it's the same name as a member variable. But yeah, just remember this, that creates a local variable. It will not set your member variable. All right. So yeah, I see that so often. It's important to make a slide and remind us all. All right. We're not going to mess that up. All right. It happens to the best of us. But yeah, any last questions about this idea before we go back to our regularly scheduled programming? All right. So let's. So we learned about the big three: copy constructor, copy assignment operator, destructor, all that fun stuff. There's now a rule of three, all right, that we should learn about, and that's why we learned them all at once, kind of, like to get to this rule, and it's pointers at the end of the day that are hurting us. So the second you start messing with memory yourself, the second you like use the heap, you're working with your own memory inside of a class, you're managing it yourself, like you're making it in the constructor, The second you do that, probably what you get from the default implementations of the destructor, the copy constructor, and the copy assignment operator, they break down. Because like if you're making memory in the constructor, you just leaked that memory if you didn't override the destructor, right? So it's the second you do something, the second you notice that, oh no, maybe I need to override the destructor or something like that. That's the rule of 3. The second you overload one thing, second you notice like, oh, the destructor needs to change. Oh, the copy constructor, I think that should change too. I want to make a deep copy. The copy assignment operator, same kind of idea. The second you notice that one of those needs to change, almost certainly you have to change the other two. All right? That's the rule. And I hope you can kind of see that from the example that we did last time. The second that happens, like you're messing with memory, you probably have to mess with memory in all these places in some way. Either get rid of it or create it to make a deep copy, all that fun stuff. And that will keep your program nice and clean and free from memory issues. All right? Like leaks or worse. Okay? So there's other kinds of rules in C++. There's the rule of 0, which is kind of nice. That was our first original box where everything actually was fine because it was just a normal int. That's like the rule of 0 where you don't have to actually do anything. Where were we? The rule of 0 is where you just like, it's going to do it all for you if you don't allocate anything inside of your class. If you use other types that themselves handle things for you, like if you put a vector as a member variable, that's going to manually manage its own memory, right? The vector type in C++ at least, that's built in. Then it'll just like, that destructor will get called automatically and your default destructor, it'll all just be fine. And so as long as you don't allocate any of your own memory, probably you can get away with the defaults. That's nice. There's also a rule of 5 that we might get to later in this class if we have time. There's a concept of, in addition to a copy constructor and a copy assignment operator, there's a concept of a move constructor and a move assignment operator when you have memory that's about to go away and you just want to like transfer it really quick, kind of. That's the secret idea. And this started in C++ version 2011 and later, and honestly a lot of people are still living in the past before that. But we'll eventually maybe get to that. All right, look it up if you're interested. There's more that we could do. All right, fancier things, but this is good enough for now. All right, so I think that's all that I want to say so far. I now want to take our attention back to vectors. The vector is the vec class that we're implementing in our lab. So I want to ask you, like, is there anything wrong with our vec class? I want you guys to discuss. Are any of those default implementations of the big 3 not right? Let me give you some examples of how we use this. Like vec v, like that's a constructor, you're implementing that. But like you are allowed to say, like you get defaults, you're allowed to say this, like make v2 from v. You're allowed to say, that's a copy constructor, call it. You're allowed to say vec v3, make it, and then eventually, you know what? Make it out of v, copy that in. Like you'll get the default copy assignment operator. Tell me, like, are there any issues with the defaults and then also the destructor? Like when you hit the end of something and it goes away, is the default destructor wrong? Like, yeah. You tell me, all right? So try to discuss, and I don't know, for fun, you guys can write it down if you'd like. You can go to the written nice page. You can elect a leader of your group. But definitely get together, say hello, and try to discuss these different ideas. Like what's going to happen right now with the defaults? Is it good or is it not good? Think about what we're doing with memory in that vec class. Could it be better? Perhaps. Yeah. The base assignment is just gonna make it and that was what happened to all of it. But you could increase to the side copy assignment. Was that enough time to think about things? Press that submit button. I'll give you another few seconds. Just trying to deal with a question on Discord. Let's see. Were we able to explain? One of us was. Nice. But yeah. Any thoughts that you want to say out loud as well? Like, feel free to keep typing and press submit. But like, destructor is not deleting the elements. That's a good thing to think about, right? Because if we have a vector, it's got that array on the heap, which we made in the constructor, and we keep on remaking potentially as we go through like the rest of everything. In the resize function, right? The resize method is going to allocate new stuff, delete the old stuff, hopefully. And so you'll always have something on the heap of some size, an array, right? And that array is ours to manage. It's on the heap. It does not go away until we say delete. Nobody else is going to do that for us. And so it's our job to put it probably in the destructor. Good. Yeah. So, and then copy constructed. The word shallow copy is a great idea. Yeah, so the second you're using pointers and heap stuff, the defaults give you shallow copies. And you probably don't want to link two arrays to one another. That would mess things up, especially if you resize one, then the other one has its own, like, what is my capacity? And it's going to really mess with everything. So that gets really weird. So yeah, good thoughts. So let's draw kind of those ideas. Thank you. And definitely, please do attendance as well. I'll stop that the next time I think about it. So yeah, they're kind of all wrong, right? Because like, let's say we've got this vector, right? It's got, among other things, all the int member variables are going to go away properly, but this array that we're making on the heap, right? That's ours. We called new on it. It's ours to say delete. So like when the destructor gets called for this v, all this memory goes away for sure. That's the point of destruction, right? That object itself and all of its own memory go away. But anything that it was pointing to, that's separate, right? That's just another address somewhere else. It's not that smart, the destructor, the default. So we have to say, no, go there too, get rid of that, yeah? And then it gets even more disgusting once you say something like this, make vec2 v2 out of v. So like if v looked like this, if v had an array, all the array is a pointer to where it begins in memory. Like, so it's somewhere on the heap. Maybe it starts at address 100, my favorite address. If you were to say this, right, make v2 out of v, it's going to set all the member variables to be equal to one another. So it's going to set capacity, num items, and array. Array is just a pointer. All right, that address is also 100, so they're both going to go right there. And now v and v2, you start pushing back. It's going to mess with the member variables of only one of those, though maybe it should not. Like it might resize, and like this one, like when you push back to v2, it deletes this and resizes it. And then this one has the old deleted address, right? That's disgusting. So we don't like that. So that's a shallow copy, no fun. And the same happens like with this, and you also leak the old one, leak the memory of the old one, right? So does that make sense? Like all that stuff. It's the same problem that we had with our little box example from last time. It's just like with an array instead. All right? So we need to fix it. We need to fix it. Let me show you the ideas in picture 4. All right, so let's talk about the big 3 for vectors to make it right. Okay, and so in your next lab, you will do vector stuff, and let me copy in. Start a code 41. I think it's 2, right? And then it's vec.h. So here's the vec.h file that you will get in your next lab. Whee! Look at all these things. So we have a few new things, right? We've got all the old stuff, resize, all your member variables are still the same. You've got the constructor, the default constructor still. You've got all these things, pushback, size, at, and sort. And then here's the big 3, right? Those are the things that we need to add. So the destructor, I want to get rid of this vector somehow. Copy constructor, I want to copy some other vector into me as I'm being built. And then copy assignment operator, I would very much like to take this other vector, bring it into myself in a nice deep copy way. Okay, that's what I want. And this no except thing just kind of promises, I promise to not throw an exception. It's kind of like const in that sense. You got to put it when you implement stuff. Yeah, so that's what it's going to look like. And let's talk about the ways that you're going to implement this, right? So, okay. Here is an example of the destructor being called, right? We've got some vector, maybe it's a local thing, a local variable called v, and we give it some values, and eventually we're done with it. We get to the end of a curly brace or like a return statement, and there, that's a good enough curly brace. And then it's time to go. So, okay, that vector v looks like this. It's got num items capacity. Those are just normal ints, right? And then it's got the array itself. And this all lives on the stack, but that R member variable is a pointer onto the heap, telling me where that array is. And this is memory I've made for myself and have to deal with. Okay, so yeah, right now, once you hit the end of this, like this part's going away, right? All of your object itself is going away when the destructor gets called, like that. All the memory associated with that object goes away. That's the member variables, but this R member variable is special. It's telling us it's got a map to this other place in memory that's also ours. Okay, that's what it means to be a pointer, and that address is on the heap, which means it's our job to deal with it. All right, so right now it's only this thing's going away. We're leaking this. Okay, does that make enough sense? Remember those words? So yeah, right now the array inside of our vectors does not get deleted when the vector goes out of scope or somehow gets deleted in some other way, like if it were on the heap. So right here, only this is happening. So that makes it very unfortunate, right? You're going to very easily leak memory. Say you had a long-running program, because some programs, they're supposed to run forever. Like, when's the last time you quit out of your web browser, right? Just imagine if it was leaking memory all the time, making vectors for like all the pages you've been to. So, like, if you do this a million times, your program will crash, right? With our current implementation, it's gonna allocate memory, and it will never delete that heap memory. So we're going to run out of memory in total for our program. So got to clean up after ourselves to prevent that. The second we fix the destructor, we can do this in an infinite loop. It would never bother anybody. Wouldn't that be great? So yeah, the way you delete your heap stuff is you go to that address, you say, hey, delete, and it's an array, right? So delete bracket, then the place with the, so R, right? And that will get rid of this, okay? So it's a very quick implementation, but it has some very important effects. Okay, so that's what's going on. That's our member variable is called R. We gotta delete bracket it. Okay, the ints are just going away with the object itself. That's fine. So that's perfect. Okay, so yeah, it's only the heap memory we have to deal with, and so it's just R, which is a pointer to a place on the heap with an int star. Right, that's the type of R. It's holding the address of an integer, which is the starting integer of that array. Okay, so that's what we want to get rid of. And yeah, just if I copy this again, the same idea, this is all we really want, right? We want to go to the heap. Let me erase to show the process, right? Before our object itself goes away, we want to say, delete bracket R. All right, That's all. That's pretty much it. That's all that we really have to do. Remember the bracket though. All right, because the second you say that, this goes away, and now we're fine. Now the rest of this is okay to be reclaimed. Okay? So yeah, the destructor implementation is pretty simple. It's just important still. Okay? Any questions about that? All right. Mm-hmm. Does the what go away? Yeah, just the whole point of destruction is any stack memory. Like this is all stack memory, right? That's kind of how you think about it. Like here's V on the stack. Your function's going away. All local memory goes away on the stack when your function returns, for example. Does that make sense?
Yeah, because I was thinking about like the structure, like default, you destruct. So like if you overload it, like does it
it does everything that it would have done in the default as well.
So like
it's an out. Yeah, you can think of it that way because the default destructor is empty and it's just going to default destruct your member variables too. It'll always do that. Yeah, good question. But yeah, if it's local memory, like this is kind of what it looks like on the stack. It's like you deal with the heap, the stack stuff's going away automatically for you. That's just how it works for function calls and things. Yeah, good question. Other questions? Whee. Boop, boop, boop. So that's the destructor. What about the rest? Copy constructor time. So, okay, let's draw some pictures. What we would like to have happen in the copy constructor is, all right, let's say I've got a vec v and I've pushed back some stuff. So here's my v. Boop. It's got an array. It's got a num items. It's got a capacity. If you think about our implementation of things, it's like we're pushing 3 things, like it's going to double the second we push this one. It's going to double again the second we push this one. So it's going to have 4 as the capacity. And we've put 3 things in it. And the R lives somewhere on the heap. So it's like address 100. That's where the start of that array is. Boop. And so it's a size 4 heap array starting at address 100 that holds 1, then 2, then 3, then garbage. Yeah. So that's up to here. And then we would like to make a copy constructor, do a deep copy. So we want to make v2 from v. We want to copy v into this new vector v2 that I'm building right now. And so the goal is, all right, what must happen? I'm making v2. I get all of its member variables. Those, like every time you make an object, you get its own member variables. It has an R that we can set. It has a num items that we can set. It's our job to set them because it's the constructor. It has a capacity that we can set. All right, so all those things exist. And I did not give myself enough room to write them. So let me fix that. Items. I should have drawn a bigger box. Just do like cap for capacity. There. All right. So first of all, what should be the num items and capacity of this new vector?
3 and 4.
Yeah. It should be the other stuff. So like the default implementation for those at least was fine. Just bring that back. Like the num items of this new vector is going to look just like V's vector. So it's going to have 3 things with a capacity of 4, though. Could potentially hold a 4th thing right now. And the magic happens for R. So what we don't want to do is like, oh yeah, copy that. So that's 100 as well, point to the same place. Because that's what the default would have given us, and that's a shallow copy. We do not like that. Causes problems. So instead, what we want to do is, okay, V, you had a capacity 4 vector, or you had a capacity 4 heap array. I will too. I'm going to make one of those. So go to the heap right now, make a size 4 thing. Like that's what our capacity should be. Go make a new one of those. All right, shiny and new, just for us. Ta-da. So that's a new place on memory, right? That's some new array. We get some address for that. Maybe it's 200. I don't know. So make an array like that with the same size, and then what you got to do is copy all these guys into these guys. Yeah. Very similar to when you were doing resize. So, okay, go through. There's only 3 things, right? There's only 3 things. So go through those first 3 indices and bring them in, right? There's no need to go through the fourth thing because that's all just like, it's different garbage, but we don't care. Right? It's going to be set by us later. So that's the job of the copy constructor. Does that make sense? How we're going to make a deep copy? It's like make another array of that capacity and copy all the old stuff over from R's, like other.R's, index, whatever. Go through it up to the num items that are there and just like bring them all into your new array of that same size. That's how we make a deep copy. Does that make sense? Those words, we can follow this picture maybe. All right, in bullet form, it's just like, all right, we have, what do we get, right? We have the other vector, it's other. We can say other dot num items, other dot capacity, other dot R. And that's how we get access to its own array and its own stuff. We go there. So like make a new int array on the heap of size other dot capacity. Yeah, that's what we need to do. And then like bring it all into our own stuff. R equals num items equals capacity equals, like that's our own member variables we're setting. And yeah, so it's other that we're going through, and just like make sure that our member variables become the other's member variables, the other thing's member variables, as long as we deep copy them when we need to. All right, so like num items and capacity, they're not pointers, so just like copy them over, that's fine. Just like bring them into ourselves, and it's like whatever was there, whatever was there, put them there too. And then R we have to be careful with, right? Because that's like, okay, that's a deep copy time thing. So, okay, make a new array on the heap with the right capacity. It's 4, right? Maybe we've already set our own capacity, just use that now. It's got to be 4. And then copy every single piece, every single element by element. You got to use a loop, right? Every element that we need to copy over, as many as there are, there's 3, right? So copy those 3 into us, leaving the last one garbage because we'll fill it later with a future pushback, okay? So that's all very similar, right? You can keep a lot of your same code and copy it in from resize. Similar to resize, isn't it? Okay, I think that's all that I really wanted to say. Does these words make sense and this picture make sense? That's my goal for you in this class. Like you're translating my pictures into code. All right, ready for the copy assignment operator? All right. Question? That's all right. That's a skill, right? That's what you got to learn. That's why you're coming to class. All right. So yeah, copy assignment operator time. So let's do it. So let's say we got two vectors, v and v2. They both got default constructed to be empty initially, and then to v we push back 2 things, to v2 we push back 1 thing. So right, the state of memory up to here before the call to the copy assignment operator, let's draw it. And again, this is great practice for you too. Like cover up my drawing. Try to draw what memory looks like, because that's another very good skill to have and to get good at. Can only help you. So all right, v and v2, what do they look like before the copy assignment operator happens? What do we get? So we got r, we've got num items. I'll abbreviate things because it's a lot to draw today. We've got capacity for that one, and then we got the same stuff for v2. What does it look like though? We got r, we got num items, we've got capacity, and okay, we have pushed 2 things to v, so that means it's going to hold 2 things. So we got capacity and num items. You think about it, it's going to double like once. So capacity is 2, num items 2, and then r is going here, and it's holding the 42 and the 43. That's what it looks like. And then v2, it just has its default original capacity of 1, but we added 1 thing to it, so now it does have an item in it. It's got 1 thing, and that 1 thing is 44. Okay, so that's what the state of memory looks like before the copy assignment. Does that make sense to us? Do we all agree? That's important. Also, I can mess up eventually, so yell at me if I ever do. So that's what it looks like now, and then I want to say v2 equals v. So bring v into v2 in a good way, in a clean way. It's not going to leak memory. It's not going to do anything wrong. That does a deep copy, right? So, okay, what needs to happen? So this array is useless to us now, right? That 44, we don't care about it anymore. It's like bring v's stuff into me now, right? So the very first step is, I would say, I'll use red. It's like, I am done. I am done with this array. Delete it. Right? Because it's not even big enough for us anyway. Right? We need a size 2 thing. So then get rid of that. Whatever your old array was, we don't care. And now, I'll go back to green. Next step, right? So now we've not leaked memory. We've got rid of our old stuff. And now essentially all we have to do is do copy constructor stuff. Right? It's kind of all that all over again. It's like, okay, I want to look like V in a deep copy way. So like my num items capacity should match. So this should be 2 and 2 now. Right? Bring those in. 2 and 2. And now my capacity is 2, so that means I need to make an array of that size, right? On the heap, size 2, int array, and then it's our job to just copy over. It's like other, right? It's always still called other in our implementation. It's like others, go into others array, and bring it all in. So like go to index 0, index 1, all the way that you need to, all the way up to the num items, right? -1, I guess. 42, 43, bring it all in, and we're golden. Does that make sense? Enough sense, at least? You do have to watch out for that self-assignment check, right? Make sure you're not going to do, like, make sure it wasn't v2 equals v2, because then, like, if you were to follow through with that and, like, you've deleted your own array, it's not good. So that is also necessary, but that's the start of it, at least. Okay? So, yeah, there's that. And so in words. So first, check for self-assignment so that you don't, like, try to set yourself to yourself. That would be wrong. If you followed the rest of the instructions, you would have deleted your own array and then tried to copy from that old deleted place, right? No good. We don't like that. So there's that, and then we've got other, right? We're trying to copy other into us, which means our own stuff is useless to us now. So we got to get rid of it. Get rid of our own R off the heap because it's probably the wrong size anyway. Okay, so get rid of that. Delete all our stuff. Because we're going to get rid of it, we're going to replace it. So it's delete R for us, and remember that's delete bracket bracket R. Remember that. So, and then it's pretty much the copy constructor all over again. So you could make like a helper method if you really wanted to. I didn't give you that ability because I don't let you modify the header file. So you're probably just going to copy and paste a lot of your copy constructor stuff into the copy assignment operator. Okay, so there's that. You can also make just like a function if you want on the fly. I don't know if that would be. Yeah, probably not. Probably would be useless because, again, you'd have to declare it as a friend. Never mind. So, and I didn't give you that ability. So, yeah, you'll just copy and paste some stuff. That's fine. And, yeah, that's pretty much what needs to happen. Now you just, like, bring in all the stuff from the copy constructor. Ideas, like bring in the num items, bring in the capacity. Now I know how big of a heap array to make for myself because I'm making a deep copy, make a brand new array on the heap of that new capacity that I've reset into. And then, all right, my array has the right size as the old array. Just go through others array, all the indices, bring those values into me. Okay? I think that's all that I wanted to say. Any questions about that process? Think we can do it? All right. Cool. And there is time, so I want you to try this now. So I'll give you plenty of minutes to try, and I think it's a really good practice, and you guys can yell at me and ask me questions as you're trying it. So here's my question to you. You do not have to give me this code, but I'm going to show you where the code from last time was, if you've not found that yet on our stuff. So you can go to like lecture 5, or you can go straight to the code from class page up here. Either way, you will get to the code from class page. Please click our class and go to the last lecture. It's the most recent one that's uploaded. I haven't given you today's stuff yet, of course. Go to the correct box file, because that's the one that like has all the stuff that we did, right? You can download it, you can copy and paste it. Probably the easiest thing to do would be to copy and paste it. Copy the file. You can also click the raw button to make it like all by itself. Then you can like Control A, Control C, or whatever. However you need to get this code somewhere you can edit it. Like there's websites for that, right? You can go on the server. Like take my stuff, and I'd like you to update the box class to hold, instead of just one thing on the heap like we were doing here, it's like int star val, please update it to hold 2 things on the heap. All right, so here's what a box should look like. Allow it to, and then give it like a default, like give it a constructor that lets you set stuff as well. So here's kind of what I want. Try this. Like let this happen, right? Let yourself make a box with 2 things in it. 42 and 43, so that should set val1, val2, as pointers to heap ints holding 42 and 43. See if you can practice like what needs to change now, because we had just a single val before, right? And we're implementing the destructor, the copy constructor, the copy assignment operator. You'll need new getters and setters like get the val one, set the val one, get val two, set val two. So it's in addition to this existing value, give it another one. And yeah, can you try to make it work, right? Because the destructor now needs to delete that second thing off the heap. The copy assignment still also needs to do that if it passed the self-assignment check. Get rid of that old thing so I can bring something new into me. And then copy constructor and copy assignment need to make a deep copy of somebody else's val2, right? So try to remember all the little pieces that need to take place here. You can use my original code as a guide. It's just like you have two things instead of one now. Try to make it all make sense. Does that make sense? The question, at least. So I'd like to give you some time to try that. I think it's really good practice, and we'll go from there. I'll give you plenty of minutes, but does everybody know where to get the code from last time? It's boxcorrect.cpp. That was the good one with all the right stuff. So give that a try. I guess you don't have to do the constructor if you don't want to. It's like leave it default to make them both 0 or something. If you want to do a parameterized constructor, that'll look like that. Up to you. Yeah, get it working.
So the brackets just check if they can very.
It doesn't check, like you have to be confident that you mean.
So how does it play like delete there?
If you delete bracket by like a single int.
Yeah, single.
I don't actually know. We'll have to try. It could be an error, or it could just like it'll notice that. Oh yeah, it wasn't.
So they'll try to delete it.
Potentially, it depends. It's probably implementation. Depends on the compiler you use. But try it. See what happens. Tell me. Do not remember how. I'm trying this. Oh, look at put that. And do yell at me if you have any questions about anything. We got plenty of time for this. Oh, that's disgusting. I'll give you a few more minutes to try it, and then I'll show you my thoughts. And you don't have to show me this code, I just want you to practice. Another minute or so, and then I'll show you my answer. Feel free to not look and keep trying. Alright, that was my timer. Did any questions come up as we were trying this that I could answer before showing you the answer? I think this will be fun. So, okay. What we want is, alright, starting from last lecture's box correct.cpp, let's copy it in to today's lecture, and what shall I call it? I will call it box with two things. That's what I called it before. All right, so it's there. Cool. And what do we want? All right, we've got, well, let's deal with the member variables first. So we got not a val anymore, it's val1, val2. Val1, val2, and let's see. How do I want to mess with this? No, I'll deal with that later. Okay, so we got those things. And now the getters and the setters don't really make a lot of sense. It's like, should be get val1, set val1, right? Same with the others, get val2, set val2. Keep those the same. And I don't know, let's do the parameterized constructor just for practice. Like 42, 43, sure. So give me a value for val1, give me a value for val2. We can make it have defaults. Like this could be a default and a parameterized constructor if we give default parameters. Like, all right, if you don't give stuff, like make them 0, something like that. That could work. And then, I mean, these are still declared the same, but they're going to be implemented differently. All right. And so once we have all those, like how do I want to be able to use my boxes? So what should they look like now? The whole point of having a constructor that kind of works like this is it's default and not default at the same time. It's default and parameterized at the same time. If I say box B1 semicolon, that's gonna, like the goal is to set the val1 and val2 to 0. I've used the same name, but they're different types for a reason. It'll get a little weird, so that'll be fun. So let's do that. Like set val1 of B1 to 42, set val2 of B1 to 43, something like that. And then copy constructor B2 set val1 to 43, set val2 to something else. Could be 44. That's fine. Or maybe this one should be 44, that should be 45. So they're all different. Box B3 equals B2. Should also watch out for the self-assignment check, right? I'm just showing us all the things that we should be looking out for when we finally fix this implementation. So this is a normal copy assignment. This is one that should not be allowed to do anything at all. And then once it's already been there, let's set all the vals to like 40, 46 for val1 of B3. Val2 can be 47. So now they're all different. In theory, if we did it right and wasn't a shallow copy, if I were to print out B1s, B2s, B3s, all of their values, I should see a bunch of different values. If it was a shallow copy and they were all pointing to the same place, then I wouldn't have all those different numbers, would I? They'd all be pointing to the same box. So that, I think, is a way to confirm that everything is working. All right, so if these print out the right thing. So, okay, see out B1, get val1, B2, get val1. Now let's deal with them all. Get their val1s first, and then their val2s. B1, get val2. B2, get val2. B3, get val2. So, all right, that should hopefully print out 6 different numbers, all right, if we did it right. And then the destructor, of course, gets called for all of those automatically. Okay, so those are those. And now we have to actually implement this stuff. So the constructor, potentially default, potentially not. You only give the default parameters once, so I need to be saying int val1 and val2 here. Int val1, whatever they were. Either they were the defaults that we got when the user gave me nothing, or they were real things, concrete values. And interestingly enough, now this won't really work. So I can't really say val1 equals new int val1, because this is now a huge problem for me, right? Because I have used a parameter with the same name as my member variable, and it also has the wrong type too. That's fun to think about. So this is going to be very confused if I wait until the body to do this. All right, so that's fun to think about. There is a way to make it work, because val1 is like it's the closer thing that takes priority. It's the parameter val1 that takes priority here. Like that's fine to make it on the heap like that, but this is not setting my member variable val1. The way to set your member variable val1, if you've shadowed it accidentally or on purpose, is to go through, if you're in the body, the only way to get there is to go through yourself. If I say this arrow val1, this is now, all right, that's a pointer to me, my own object, and this must be a member of that object. That's a member access operation. That's forcing me to get val1 like that. This is forcing me to get val2, and then I'm setting it to the parameter val2 with a new int on the heap with that value. Okay, does that make a little bit of sense? That's necessary. If you want to do it in the body, we could also be cool kids and do it in the initializer list where it does not matter. Like you say val1 first, like that's our member variable. The second you say that, the very first thing is always the name of a member variable. And then what I want to set it to, a new int on the heap holding the val1 parameter. Now the second, like whatever goes in the body or in the parentheses is whatever is like currently really in scope, whatever takes precedence, which is the closer thing this is now shadowing. All right, so that's another way to do it, because the second the first time you say like anything, this is always a member variable name. Val2, set it to a new int of the val2 parameter. All right, so that's the moral of that story. All right, those are two different ways to do it. Either way will work, and that will set my boxes val1 and val2 to pointers to integers on the heap with these particular values. All right, that's what's about to happen from whatever I was given. If I didn't give anything to my box constructor, it would be holding 0, 0. If I gave stuff, it would be holding something else. So that's pretty nice. And now we're ready for the other. So get val1 is like go to val1 on the heap. Same with get val2, go to val2 on the heap. Give me that value back, that integer that it's pointing to. And then same with set val1 and set val2. So like we're going on to the heap, getting those values, messing with them. And so that's val2, val2. Those should all be fine. Yeah, just stop me when you have a question. But okay, this is what the declaration looks like. Again, we got val1 and val2 on the heap now. So the destructor is a bit different, right? Let's see, how do I want to deal with that? I guess I want to not get rid. I want to get rid of these calls because this doesn't make sense anymore. Get rid of all these cout things. There. So the destructor, the things on the heap need to go away. So it's val1 and val2. So delete val1 and val2, right? That's what we should have noticed. Does that make sense? Like there's two things on the heap now. There's those. And now copy constructor. Okay. We need to make a deep copy. So we got some other box. It has its own val1 and val2 pointing to places on the heap. I would like to make my own val1 and val2 also pointing to places on the heap that are different. Deep copy, all right? But bring in the value for those things. So like my val1, make it a new int on the heap, but holding that int that it's really pointing to. Let it hold the other's val1, the integer though. Like get to it, follow that pointer in val1. Does that make sense? Like that's what we need there. Same for val2. Questions about that? The syntax might look a little weird, but like that's the whole reason we're practicing, right? So there's that. Exactly the same idea for the assignment operator. It's just like, okay, check for the self-assignment, of course. Do nothing if you're trying to copy yourself into yourself. And you check that by saying, like, is my own address, the address of me, equal to the address of the other object I'm trying to copy? If so, I don't need to have an identity crisis. I can just do nothing. All right. And it's always you return a reference to yourself by saying return star this, because star this gives you yourself, and then if you ask it to be a reference, it'll just convert it on the fly as it's returning. So that's perfect. All right. But then copy assignment's job is like, all right, I have my own member variables, val1 and val2, but I don't like them anymore. I want to bring some other stuff into me. Technically, you could just like go to your existing places on the heap, but like this. The way that I'm telling you how to do it is like going to help you for the vector implementation. So let's just delete stuff. It's like we're done with ourselves. Delete my val1, delete my val2, and then do exactly the same stuff as I did in copy constructor land. It's like, all right, my val1 is now a brand new place on the heap holding the other things val1. Same with val2. All right, so go and give me ints that look like those, please, and again, return a reference to ourselves. Return star this is always what you're going to be returning in a copy assignment operator. Okay? And I think that's it. This v plus 1 thing is useless. Not part of the example anymore. But yeah, that's the declarations. Really only that's changed. All these are the same, but the implementations, of course, are a little bit different. That's the most complicated one. Are there any questions about what needed to change? You added a second thing on the heap. So yeah, this would be fun to stare at probably. But let's make sure it prints 6 separate values, at least to confirm that there was no, like we didn't do a shallow copy accidentally. It looks like I see 6 separate numbers, and that's what we wanted to see. Good. You can also confirm that you were cleaning up your stuff properly by checking for memory leaks. That's called val grind. There's some on one of the slides. I said which one it was. Like it's val. What you say? It's like you pretend to run your program, but at the start you say val grind dash dash leak check equals full. It's like all heap blocks were free. No leaks are possible. Great. So we're still remembering things. If I forgot one of these, then it would yell at me. If you did a shallow copy, you try to delete the same thing a few times, it would also, that would be a runtime error, in fact. So that would be even worse. But yeah, I think that's the example that I wanted to give. Is that what we got? Did we get close enough to that question?
Yeah, kind of different syntax related question. But instead of doing the asterisk other dot, could you do other with a little arrow?
Let's see here. No, because other itself is not a pointer.
Okay.
Other would have to be the job of what the arrow does is it does this. If I were to say star other dot val, instead of that, if I were to say other arrow val, what it would do is it would turn into star other in parentheses dot val. So other would have had to have been a pointer. Does that make sense?
Mm-hmm.
Sadly, but no. What we're trying to do is what we get without using parentheses. Like do that first. Go to other dot val. Now that's the pointer. Dereference that. It's kind of backwards. See it? Yeah, good question. Other questions? All right. I think that's all the code that I wanted to write today. I just have pictures now. Yeah. So, we ready for a completely different idea? Or a few completely different ideas. All right, so I trust that you can implement the vectors properly now. So what I want to do for the remaining time today is just, I want to say some words so that you've seen them or heard them once. I'm not gonna I'm not ready to test you on any of this stuff. I just want to go through all of the data structures that we're going to learn in this class. I'm going to tell you their names. I'm going to tell you kind of how they work so that you will have seen them once. You'll have a picture in your mind maybe when we get to them. That's the goal. So yeah, let's talk about every single data structure we're going to deal with in this class because that's half the class, right? Data structures and algorithm analysis. So okay, arrays. That's a data structure, right? We know about those. We know them very well. I don't have to say anything else, really. It's just what is an array? What does it look like? It's something with one name that holds a bunch of values of the same type. So this is what it looks like. That is the job of an array. And it's a bunch of things with one name, and they're all next to each other in memory. So if this is an array of ints, 1, 2, 3, whatever, then if you know that the array starts at address 100, the next int is at address 104. You know that because integers are 4 bytes long. That's the next contiguous address place in memory 4 bytes later. This wouldn't have to be at 108, etc., etc. And so ints are great because you can, arrays are great because you can go to a place, because you know it's contiguous, you can very easily calculate the address of a certain index without having to make your way through the array or anything. So all right, I want to go to index I. So it's starting at index 0, that's that address. Calculate what address I need to go to. I know where it's going to be, so I can quickly go there and in a very short amount of time. So very quickly, I can get to any piece of an array because I know they're all right next to each other. That's the beauty of arrays. All right, it's all contiguous, and that's what gives me that power. All right, so that's pretty much all that I need to say. You already know about arrays. So there's that. You can make them on the heap, of course. The next one, let's talk about linked lists. You may or may not have heard that phrase before. So I forced my CSCI 40 students to read about linked lists at least, but not actually implement any. We are going to implement linked lists in this class. So if you've heard of them, it's okay if you have not heard of them. This is what they look like in memory. These little things, boxes with arrows everywhere, so pointers all day long. So arrays hold a bunch of stuff in a contiguous, in an order, and they're contiguous in memory. Linked lists also hold a bunch of stuff in an order, but they're not contiguous in memory. They can be in some weird way. It's kind of you have to follow from the start to get to where you want to go. So there is a list type in C++. There's a list header. It's include list. You can make a list of ints just like you can make a list of vectors. We're going to do something like that. Every list is made up of a bunch of things called nodes. These are what nodes look like in a linked list. They hold, the goal of this list, by the way, is if it starts here, this is the first node in my list. You're going to use pointers all day long. This is the first node in my list. It's going to hold data. So the job of this list is to hold 30, 47, 53, 26, 74. That's the list. That's the ordering, just like an array, kind of. It has that order from start to end. Like there's a concept of first, and there's a concept of like last. And then the way you get to places is that each of the nodes they hold, in addition to the data they're holding on to, like that's 30 at me, the first node of the list, they're also going to hold a pointer. They're going to hold a pointer to wherever the address of that next node is. That does not have to be contiguous at all. Just somewhere. They're usually going to be on the heap. So that's where that's going to be. And so like the next node is this place in memory, and you can dereference that to get to that next node. And then now it has some data, and it has a next pointer. All right. So if you think about implementing this, it's kind of interesting. It's like every node looks like this. It's a struct node to make the type. Inside of every node, all those orange things in the picture, it's like every node has a piece of data and it has an address of the next node in the list. So let's say it's a list of ints, so like it's got some int data. And then it also has something called next, which is a pointer. What type should I be putting there? No. Something that's other than int. Because what is this pointer taking me to? If I were to dereference it, it gets me to this whole thing, doesn't it? What was it? There's another node. Weird. I'm defining nodes within nodes, aren't I? That seems a little circular. That seems a little potentially dangerous. But no, that's fine. Because the fact you have a pointer here, it does not get like infinite and weird. It's just an address at that point. So that's what it looks like. Those are the types involved. And so nodes are defined in terms of pointers to themselves. It's weird to think about. I love it. So look forward to that. That's what they'll look like. You dereference this address, like, all right, I'm at the first node, get its .next, dereference that to get here. I can look at the data and then also keep going, right? Keep going in a loop, get the .next, give me that node. That's how you can go through your list. You got to follow those next pointers all day long, all right? Which may be disgusting to you right now, and that's fine. The job of a linked list, the reason it exists, the reason we care about learning about linked lists is like, yes, it is a competitor to arrays, right? It's holding numbers in order or something, some piece of data in order, just like an array could have, but they're not contiguous in memory, which lets you do some interesting things. Imagine you had a giant array with a million things in it, all filled in, and you would really like to put something at index 0 and keep everything else. Say you had some room on the end over here. What would you have to do? You'd have to shift every single piece of those million elements over by one, wouldn't you? To bring in new space here, and then you could put your thing there. The longer the array, the more time that would take, right? That's disgusting. Watch how simple that would be with a linked list. There's trade-offs. There's definitely trade-offs going on. So that's why we learn about them. So like, let's say I would really like, you pretend this list was like 1 million nodes long. Who cares? Let's say I'd really like to put something in between the 47 and the 53. Watch how simple it is. It's like, all right, I'm going to make a new node on the heap. I'll put the data holding 42. I'll put the next node being this one, because I can get its pointer from here. That's fine. And then I can just say, okay, 47, your next node, it's not this one anymore. Drop that off. Bam. It's now this one. Kind of 3 steps. Doesn't matter. It's happy. No matter how big the rest of that list was. I can just put it right there. It's the beauty of pointers. So that's linked lists. If you have any questions, you can shout them out. But again, I'm not ready to test you on this or anything. This is like, we're getting there, right? This is where we're going. So there's that. That's a data structure we'll study hard. That'll be one of the main first ones. And then, all right, another one's called a hash table. Maybe you've heard of that. Again, you don't have to have heard of it. I'm going to teach you it in detail. A hash table, at least in C++ land, there's always something that's pre-implemented for us. Like we got lists, list event. The C++ standard template library version of hash tables is called an unordered underscore map. It's a little long, and it takes 2 things. Like it takes a type for keys and a type for values, like string to int, for example. Table. So this is the first type you give here is the key type. The second type you give here is the value type. And the job of a hash table is to be a lookup table. It's a lookup table at the end of the day. Lookup table. And so it's actually implemented as an array, a fancy array, but in a weird way. So the job of a hash table is to take you from some arbitrary type that is not an integer into an index of an array where you hold things, where you hold all your values. So like a good example of a hash table in real life would be like a phone book. Like a phone book, remember, like, hopefully we all know what those are, even though they don't really exist anymore. It's like you can look up by somebody's name what their phone number is. That's what a hash table lets you do. So like you give it a string, you give it a key, it will, through some fancy math called a hash function, give you an index where that you can go and find the phone number, which is an int. That's kind of how that works. It's going to take you from one type to another, Like you're using this key type to look up a value. That's what that does. It's really taking you to an index somehow. Using a string to somehow compute a number that is the index where you store something. Like Lisa Smith is apparently, the hash function takes you to index 1 of the hash table. That's where their names, their phone number is going to be stored. So it's some type to some other type. That's what a hash table is. It maps you from somewhere to some other place. Okay, like this one takes you to 1, 4 apparently. Like somehow you have a way to turn a string into a number, because that'll give you an index, and you have a bunch of ints at those places. Those are your values that you're storing. So it's key type, value type. All right, and there's no real concept of order. That's why it's called unordered map in the C++ library. So it's like a string takes you to an int. You could have had anything here, like a double takes you to a string. It doesn't matter. Somehow you're calculating indices, and that's what we're going to deal with. Okay, so that's a hash table. It's like a lookup table. You take some type to some other type. You can look up one thing, look up the keys, and map them to values. So those are those. Next, if you didn't like linked lists, you're going to hate binary trees. This, instead of at each node you have 1 pointer, you're going to have 2 pointers. So here is what a binary tree kind of looks like. It's called a tree because if you turn it around, it kind of looks like the branches of a tree, or if you keep it right side up, it looks like the root system of a tree. Whatever you want to think about, that's fine. And binary trees are awesome because they let you like order stuff pretty easily, or and move around in a cool way. So like there's a concept of like where the tree begins instead of like first and last, like a linked list. We call it the root of the tree, which is fun. I love the metaphors here. And then at every node, these are our nodes of a tree. It's not just next, there's left and right. You can go left, you can go right. And you can put special things on special sides. Okay, so this is what a node looks like for a binary tree. Struct node. What do we got? We've got some data. Every node holds some data somehow. Let's say they're ints this time. Int data. We've got now pointers to other nodes, so node stars again, but it's not called next. It's node star left and node star right. I hope you can kind of read that and understand it. Node star right, and that's how you can move around your tree. If somebody gives you a pointer to the beginning of the tree, which is the root of it, you can follow left and right stuff all day long to get to where you need to go. Okay, so that's what those are. To mark, should I have said that here as well? Yeah. To mark the end of a list, you could store the address of that of that node. You could also, what we do is we put a special value at the end of a list as well. Like there is no next. To mark that, we give an address that nobody could use. We give the null pointer. So that's the 0 address. So that's another way that we mark the end of a linked list. We give the null pointer there. I'll draw it as a slash. Same idea with binary trees. To say that, oh, there's nothing below me in the hierarchy, you say the left and right, they're null. Don't try to dereference null, of course. You got to check for that. It's like the right pointer of this 9 node is null. It's the null pointer. So that's kind of nice. That's useful for us. But otherwise, you can move around as long as you have something to go to and say, like, same for these guys. Null left and rights. So a binary tree, because you have options, you can spread things out. So it's very fast to search through. Faster than some of the other things. Fast to search through if you want to find something. And then also, you can keep track of order if you wanted to. You can have a sense of order. Like you can store stuff in order if you wanted to, where you put smaller things to the left and bigger things to the right and keep following that pattern. Like that would make it easy to find something, right? And so we'll play that game eventually. but that's a binary tree. Any questions about that? Does it make enough sense? So that's where we're going. Yeah.
Is it possible to have the ranges reconnect at some point in the binary tree?
You're not supposed to do that.
Okay.
Yeah, that would make it very hard to search for things and know that I didn't find something. Because like the goal of when you're searching is like, was it there or did I get to null? Kind of.
Well, I mean, like,
Is that what you meant?
Connect 11 to 4 or something.
Oh, something like that.
Yeah.
Yeah, there are some implementations where like, it's really cute. You think of it like a binary. You think of it like a genealogy. So like these are siblings of one another. Some people like they do put pointers of like get to other places, get to my cousins on the same level kind of things. Like that's a possibility, but it adds complexity at the same time. Yeah, that's definitely something that people do. Depends on the like what you're going to use it for though. Sometimes this is enough. Sometimes there's a pointer to the people above you that they're called your parent node. These are its children. It's so very cute, all the metaphors. So yeah, let's look forward to those when we get there. Another kind of binary tree that we'll care a whole lot about is called a heap. And this one has a sense of order. You can kind of see it here. Unfortunately, this is an overloaded term. We know about the heap, right? That's just a place where we it's like a pile of memory for us right now. Heap, the data structure, has absolutely nothing to do with the heap in memory, okay? That's dynamically allocated stuff, so we'll have to keep that separate in our brains. But the job of a heap is to keep track of, like, something important for us. It's like you put a bunch of stuff into your heap data structure, and the thing at the root, the thing at the top, is always, you can do two kinds of heaps, at least those are the two kinds I'll teach you. The root of your heap is always going to be either the maximal thing or the minimal thing. Always maximal or minimal. You could have a max heap or a min heap, we say. This is an example of a max heap. Do you see how at each level, like the things above are always bigger than the things below? And if you play that game, you're guaranteed to have the biggest thing at the very top, aren't you? So you always know, always have a good handle on what the biggest thing is in your heap data structure. That's really cool to think about. If you did the flip of that, you'd always have the smallest thing at the top. And then if you want to like pick them out one by one, like get rid of that, bring in the new thing, like there's an algorithm for that. We'll talk about it. But that's really cool, right? It's like everybody wins out. It's like once you get rid of the 90, for example, the 89 is going to take its place. It's going to like rearrange itself. And yeah, it's a binary tree still. You can go left and right, up and down, and it's very, very fast. I think you can imagine, because you know exactly where it is, very, very fast to extract the max or the min, depending on which one you're using here. In this case, in this picture example, it's the max. That's fun. And then it's also very quick to like get rid of that and like bring in the 89 to where it needs to go and all that. So yeah, those are heaps. That's another data structure. And that's more or less the ones we're going to study. We'll talk about the abstract data types that are associated with all these data structures. Like what could I want to do once I have these? Like what are the operations that I would want to be able to do? Like add a thing into the heap, give me back the max or something, like those kinds of things. Like that's the flip side of it. We'll get there. But yeah, the whole reason we have this class is because there's more to know, right? You can't just get by with arrays and the heap for the rest of your life. There's better ways to do things. Question?
Are there trees that point to more than two?
Absolutely. Those are just called trees at that point. It's not a binary tree anymore. Like you have three. Yeah, then you'd have to have like, you could have a list of children, a list of people below you, or a vector of people below you. Then you have options. Yeah, you have to call it something other than left and right. Yep, you can definitely do that. You'll study that more in CSCI 26. At least that's when I force my students to deal with that. Yeah, good ideas, good thoughts. So yeah, the reason we're learning all this is because like, I hope you can kind of see the trade-off, at least, between arrays and linked lists. Like the way that you can add something very quickly into the middle, whereas with an array that's very, very hard to do. You're giving up power for other power, I guess. There's always trade-offs to all these different data structures. And so when you're tasked with something, you want to pick the one that's right. You want to pick the one that gives you the best bang for your buck, that gives you the least amount of issues and the most amount of like success and good things. So yeah, these data structures, we can make some very cool abstract data types that do cool things, perform cool operations, and each of them is good at a couple things, not everything. So there's always trade-offs to consider, all right? Some of these things don't even support some operations. Like a hash table has no idea of like, I would really like to go through these phone numbers in order. That kind of ruins everything. It can't even do that. So like some things you can't even think about. Like you're not meant to think about it like that. But what it can do, it's very good at. This kind of stuff. So yeah. And each of these things will have different computational complexities. Like it'll take some memory to do those operations. It'll take some time to do those operations. And if your boss gives you something you need to implement and like here's the list of things it must do, like you want to pick the one that has the smallest amount, uses the smallest amount of space and gives you the most amount, the fastest like execution time as well. All right. So yeah, in general, the reason we're talking about this now is like this is what your job is in this class. This is my goal to teach you, like if you're tasked with something, figure out like what are the right data structures to use and how to combine them, because maybe one is not good enough. Like I need a binary tree, and at each node, I want to store not ints, but I want to store hash tables or something. I don't know, something like that. Like you can combine them, and that will give you the ultimate power, right? So that's going to let you solve your problem in the fastest, most efficient way possible. And yeah, that's the goal. You'll be peak efficiency. You'll get the job done as fast as possible. You'll be praised by your boss or whatever. And yeah, I think that's all that I wanted to say. Are there any questions about that? Philosophy to end us. So, okay, that's pretty much the end of these slides. We'll start some new ones next time. We get a long weekend, but this is a Tuesday, Thursday class, so you're forced to have 2 lectures till next week. Remember to come here on Tuesday, even though there's no class for you on Monday if you have a Monday class. And now it's time for Lab 2. So this we do the 5th, so that's next Friday. And this, I can't remember, this may be the one lab in this class where you really got to do the one before it. Like you have to do it well, because it won't work, right? I'm going to ask you to copy in your stuff from the old vectors lab. All right, this is vectors part 2. So definitely get vectors part 1 good, otherwise this won't work. Otherwise none of the tests will pass, because you need pushback working, for example, stuff like that. So let me show you that code. You'll do the gimme command to get it yourself. Start code 4102. But here's what it looks like. You got all these fun things. And let me show them to you. So you're going to implement the big 3. Honestly, I don't have to say much. You're going to implement the big 3 and copy over your other stuff. So like vec.h looks exactly as I showed it to you today. That's the one that you're getting in the lab. So all these fun things. The additional stuff is the big 3. There they are. You're going to implement those in vec.cpp. Boop. And so like here's the new stuff. Like you'll implement these. You'll do it right. I've done it for you, more or less. Again, this is just a line. Whenever I give you something, like this is a line that just lets it compile right now. If you're not ready to work on this thing, this is absolutely nowhere near close to being correct. Just delete that line entirely, all right? It's disgusting. And then for all the other stuff, just copy in everything that you did from the last lab. You may notice that maybe you accidentally did something like that leaked memory or something in your last lab. Like you'll have to deal with that eventually, but just copy it all over for now. Most of it, if you did it right, it should all be like you can keep it the same. So yeah, the new stuff is there. So I've told you in picture form and word form how to implement those things, and so you'll fill it all in the right way. Remember your self-assignment check and the copy assignment operator, and that's pretty much it. I got a test vec for you again. I've got a make file that compiles it all. So here, the make file. There's a couple of different make files, or there's one make file that compiles 2 different things. So we got test vec. As before, here's some tests. I want you to make your own as well, 4 more tests. But here are 2 tests that test the copy constructor and the copy assignment. The destructor is just kind of implicitly called no matter what anyway, so like they're technically testing that too. So this one's making some vectors. There's copy constructor call, making sure that things are being copied and changed correctly. We're not doing a shallow copy. There's that. Copy assignment example, just to test to make sure everything is as it should be. yeah, so get those tests to pass, and you'll add 4 of your own. All right, so come up with some wild scenarios, but add 4 more assert true calls, please. So you should see passed printed 6 times total for this test file. Does that make sense? And so that's test vec. You say make test vec for that, and then why go through the trouble of making a vector if we're just gonna like test it and just make sure that it works for numbers and silly stuff like that? That's silly. That's not as cool as it could be. So what I've done is I've made a silly little file that is called calc receipt, and this is pretending to use your vector to actually do something that might be useful. It's like we're pretending to use your vector class like at in and out or something on the cash registers to like remember all the things that you've ordered. All right, so I'm going to calculate a receipt by using our vector class. So here's what it's doing. And you can compile this program. It's using your library still. So you say make calc receipt. That's the name of that recipe. So here's that. And so here is this file. And what I want you to do is you're going to implement this. You're going to get a vector of prices. You're going to make a vector of prices given all the things that you're asked to like save in the cash register. These are the things that the customer's ordering. Okay, so again, this is a use case, we call it, for our vector class. We're actually using it to do something useful. What we will do is read a file. So you're going to have to remember how to read a file. Passed along in the command line arguments that represents a receipt. So this is how your program is going to be run. You're going to say /calc receipt, and you're going to get this file name given to you in the command line arguments. So that's this right here. Let's see, how do I want to say that? That's good enough. So that's these things. I've already done it for you, so don't worry. It's argc and argv for main. If you've never seen that before, you might want to look that up. But I've kind of already done it for you. I'm getting it. It's argv of 1 that holds this file name. So like I've already set it up. I've already given you the file, the ifstream object. So that's hooked into the correct file now. And your job is to go through every line of that file. I've already set that up for you as well. Like I've given you a loop that goes through every line of that file. Every line of it is getting set into current line. And the job of your program is to read each line of the file that you're given. They're CSV files. That's something you can open up in like Excel. It's called comma separated value files. Like here's an example that you'll give it. It's like everything exists and then they're comma separated. So like what your job is going to be in this implementation is like you're given each line one by one, and then you're going to extract the number part, because that's what you're going to put into your vector, because it's a vec of numbers, right? So your job is to go through and get the price out. It's the second column of every one of those CSV files that you could possibly be given. All right, so you're going to have to go look for, like you're given a string, right? It's just a string that is the line. Go look for that comma, because that tells you that the price is coming after it, right? So think about how you'll implement that. I've given you 2 of these files, right? Order 2. So think about that. Extract these. You're getting them as strings, right? Because it's a string. Every line is a string. These are supposed to be numbers as you place them into like cents amounts rather than dollar amounts. You'll place those into your vec of ints with pushback, but pushback works on ints, right? So you're going to have to convert a string to an integer. There's an S2I function for that. There's other ways to do it. You can pick any of them as long as it works. All right, but your job is to go through this file line by line as I've given it to you and push back each of the prices you find in the file. Does that make sense? Like that's what you're pushing that into your cash register program, and then your goal is to then iterate through your vector. Actually use your vector for once, right? Iterate through your vector, print out the sorted price, as you'll call sort on it, right? And then print out the full total as well as you've gone through it all. So like if this is order.csv, you've got all these things, print it out in a pretty way, make it be, even though it's given to you in cents, print it out as dollars, right? Put a dot there, and then print out the full total after a line of 6 dashes, and remember to place dollar signs at the start. Does that make enough sense? Like you're actually using your vector to save these, right? Save them, iterate through in sorted order, build up the sum, like you're actually using your vec as a vector. Yeah, that's my goal for you. So just get that working as well. Okay, so I've given you most of that stuff. It's just like, just extract the price from the file, from each line of the file, sort it, iterate through it, print it out. I've given you a few hints. You may or may not need to use them, depending on how you think about implementing this. But yeah, you're getting a file name from the command line arguments. That's already done. Like, you've got IFS to use. I'm already going through each line for you. Just like in this body, you're getting every current line has been set to the next line of the file. Deal with it somehow. Okay, so that's that one. Any questions about calc receipt? So it's make calc receipt. That's the name of the makefile rule that will build that for you to compile and run it. Like, that will like link everything properly. And then that's separate to make test_vec. Those are two separate files with main functions in them, right? Two separate programs to run. You got your test_vec, you got your calc receipt, and yeah, so that's that one. And I think that's all that I want to say. So don't forget the tests, right? You got some new tests to create in testvec.cpp again. And I think that's everything. So what you'll be turning in then is your library implementation. You cannot touch the header file. You got to keep that as it is. I'm testing you with the original. Your updated testvec with the old existing tests as well as your new tests. So 6 total, 4 new ones. And then calcreceipt.cpp implementation of you like remembering how files work and actually using your vector class for something that is what a vector class should be used for. So yeah, I think that's what I wanted to say. That is your lab 2. Are there any questions about any of that? Does it make enough sense? So yeah, follow the pictures as a guide, and I believe in you. So with that, I believe that's all for the day.